2010, quiz number 2, problem 2, bit balancer. In an effort to monitor the obscurity level of their encoding techniques, a super-secret government agency has asked you to take over development of the bit balancer. The BB, as it's called in this agency, is a simple synchronous FSM with a single input and a single output, which is 1 if the input has been a 1 during exactly one of the last 2 clock cycles, i.e. if the last 2 inputs are either 0, 1 or 1, 0. So on startup, the bit balancer should behave as if it's received only zeros thus far. Your predecessor in this job was Chip Ahoy, who got a C in 6004. Chip struggled for hours and finally demonstrated a 5-state FSM that behaves according to the above specification. Unfortunately, the state transition diagram he left you is incomplete. In its initial state, A, this assumes that only zeros have been entered. Your first task is to complete Chip's diagram and make his finite state machine work. What are the appropriate values for the outstates of C and E? Okay, so we were told that the output should be a 1 if it's had a 1 and a 0 for the last 2 inputs, right? So starting in this initial state, A, we have 1, and then we have another 1 if we're going to C. So for C, this indicates that the last 2 inputs were 1. So we want the output to be 0. Now for state E, go like this, we had a 1 and then a 0. So for state E, the last 2 were 1 and then 0. So we want the output for state E to be a 1. So if we want to fill in the missing state transition diagram for state C in the above diagram, we see that there are arrows, there should be an arrow going out of state C for both of the possible inputs, right? We should have both cases covered. So right now, it seems like we've only got this 0 case covered, right? We only know what to do when the output is 0. So we need to determine where it should go when the output is a 1. So we said that state C corresponds to the last 2 inputs being 1. So if the last 2 inputs were 1, 1, we're in state C, right? And then we get another 1. Well, then the last 2 inputs were still 1, so we should stay in state C. So we'll fill in this and put a 1 right there. Now, on part C, we're given an incomplete truth table for this finite state machine, shown to the left. So if we want to try and determine which state is which, we can start off by looking at the fact that in state 0, 0, 0, the input is a 0, and then we stay in state 0, 0, 0. So that must be state A because we have this arrow right here. So this is 0, 0, 0. Okay? Now, so if 0, 0, 0, so that's state A, has a 1 on the input, then it goes to state 1, 0, 0. So a 1 from state A. So this one, state B, must be 1, 0, 0. Now, if we're in state 1, 0, 0, and our input is a 0, then we go to state 0, 0, 1. So E is 0, 0, 1. State 0, 0, 1, input is a 0. We should go back to for state 0, 0, 1, input's a 0, we should be going back to state A, so that's 0, 0, 0, and our output is a 0 in that state. Okay, so if 0, 0, 1, we receive a 1 instead, then we're going to go to D, so 0, 0, 1 receives a 1. It should go to state D, which we don't know the bits for yet, so we're going to hold off on that. But we can determine by saying state D, we know when it receives a 0, it's going to go to, quote, 0, 0, 1, right? So, this one, when it receives a 0, goes to 0, 0, 1. So this must be state D. So this must be 0, 1, 0. So here, this must be 0, 1, 0. Because when E is 0, 0, 1, it goes to 0, 1, 0, which is state D, and the output is 1. Okay, so now I think we have some information to answer part C. It says, what are the 3-bit state assignments for state B and for state D? So for state B, we determined that was 1, 0, 0. And for state D, we determined that was 0, 1, 0. And it also says, what are the missing next state values for the state encoded as 0, 0, 1? So that would be state E. And we just figured those out right here. So the next state from 0, 0, 1 when the input is 0 is this one right here. So that's 0, 0, 0. And when it's 1, that's this line, so it's 0, 1, 0. And we're done. Okay, so this is page 2 of problem number 2. We ask, while rummaging through one of Chip's abandoned desk drawers, you come across the following circuit diagram labeled another BB solution. You're struck by the simplicity of this circuit, which consists of 2 flip-flops and a single XOR gate. You dimly remember from a 6004 lecture that the 2 flip-flop circuit has at most 4 states, which makes you wonder if Chip's 5-state FSM has more states than necessary to satisfy the BB specification. So for 1 point, does the 2 flip-flop circuit function as a BB FSM? Either circle yes or give an input sequence for which its output differs from Chip's original FSM design. So if on the first clock cycle, this guy latches a 1, then on the second clock cycle, that 1 will go here, and a new thing could be here, like say a 0. So that means that if we get a 1 and then a 0, this XOR will see the 0 and see the 1, it'll output a 1. If this XOR sees in the last 2 clock cycles we had either a 1 and a 1 or a 0 and a 0, which should output a 0. So it looks like this does function as a BBFSM. Great. Stimulated by the above possibility, you look again at Chip's original FSM design to see if there are equivalent states that can be merged to yield a smaller equivalent FSM. Chip's state transition diagram is reproduced here, and we can assume that it's been completed as to your parts of A and B of this question. So remember, we had an arrow like that when we figured this one out. So we want to know if there's an equivalent pair of states that can be merged in the above diagram to yield a 4-state FSM. If so, what are the equivalent states? If not, circle no. So it looks like there are 4 different state possibilities, right? This is, the last 2, bits were 0, 0, 0, 1, 1, 0, and 1, 1. So if the last 2 bits were 0, 0, we said that that was what happens in state A. And if the last 2 bits were 1, that's state C. Now, if we had 0 and then 1, we'll get to state B. If we have 1 and then 0, we should get to state E, right? So how do we get to state D? Well, we can have a 0 and then a 1, right, from state C, 0, 1. And it looks like that's the only way to get to state D, and it looks like that's the same thing that you can get to state B. So it looks like B and D are the equivalent states. So we can just get rid of that.